Okay, so I think we are all ready to start. So welcome everyone to this junior researcher webinar. Today we will hear the presentation of Nathan Giha, who is a postdoc at IJCLab. And today he will present his PhD work on the measurement of spin energy correlations in nuclear fission.
All right, thank you, Lori. Like she mentioned, I'm a postdoc at IJCLab. I'm in the nuclear astrophysics group, but prior to that, I did my thesis work at Argonne National Lab, measuring correlations in fission. So that's what I'll be talking about today. And I have on the beginning slide a photo from before the experiment we conducted, where we have this 3D printed version of our fission chamber, just for aligning the mounting inside of Gammasphere at the lab. Uh, Here's another picture of the real one with a glass window for even more mounting reasons. I don't know, it kind of looked funny to me. So the presentation is organized as follows. I wanted to give some background on fission since we may have different levels. And then I wanted to give a little bit of a literature review on fission gamma ray measurements. Of course, fission's been around for a long time, so we can only scratch the surface, but there are a few that I wanted to highlight because they're relevant to this work, which is a Californium spontaneous fission experiment at Argonne, and then some conclusions. So I asked ChatGPT to give me a nice picture of fission, and this is what it came up with. I guess it could be worse, but there are some big problems with this, and hopefully by the end of the next few slides, you'll be able to diagnose them. But first, some history. So in 1934, which was at this point several years before fission was discovered still, Enrico Fermi was looking for transuranic elements, and maybe a natural way to try to find those is to take uranium and bombard it with neutrons. Hope that the neutrons stick to the uranium and you have something heavier. He found something that wasn't uranium, so he thought he had added a neutron and maybe it beta decayed and it was something heavier. But one of his contemporaries, Aidan Nodak, was actually maybe the first to suggest fission. And in this case, she was right that that Fermi was actually causing fission rather than making transuranic elements. In late 1938 and early 1939, and in quick succession, Hahn and Strassmann discovered fission in Berlin, and then Lisa Meitner and her nephew Frisch gave the first physics interpretation. Actually, later in 1939, there was this Einstein's Szilard letter, where Einstein signed a letter addressed to the current president of the United States, Franklin Roosevelt, where they said it was possible that a weapon could be made with this new fission technology, where it might come in on a boat and explode a port, but probably too heavy for transporting air. We see later that they were a bit off the mark in that one. In 1942, the first technological triumph with this newly discovered reaction was the world's first artificial nuclear reactor. But at this point, we all know how this story ends, or rather, maybe begins. The United States uses fission as a weapon. They detonate 2 bombs over Japan in August of 1945. And after that, the fission is entrenched as a dual-use technology. It's been studied a lot since for peaceful reasons and for not so peaceful reasons as well. But back to the physics. To first order, you can think about fission as a charged droplet of nuclear matter that elongates in splits. And there's this nice paper by Bohr and Wheeler where they do some calculations of from just a simple liquid drop model, and they actually get not too bad results for things like the Q value. And this idea of the liquid drop splitting is kind of illustrated with the shapes here. The idea being that there's this competition between the strong nuclear force and the Coulomb force, and at some point during the elongation, it becomes given that the nucleus is going to split. Now, the reason that fission happens in the first place for heavy elements is that you gain energy by going up on this binding energy per nucleon curve, and for fissioning systems, we're over here. And I wanted to give a small cartoon just so that we know some important terms. Usually, when fission happens, there are two fragments, and they are emitted back to back in their center of mass frame to conserve momentum, and the axis on which they're traveling is called the fission axis. They, of course, have their own charges and masses. They have a certain amount of kinetic energy, excitation energy, and also spin or angular momentum. And for californium-252, spontaneous fission, and these values will be somewhat similar for low energy fission of other actinides. You might have fragments that look like this: molybdenum, barium, kinetic energies on the order of 100 MeV or a little less, a little more. Excitation energies, you can have tens of MeV of that. And in a given fission event, you might get 3 or 4 neutrons, sometimes 0, sometimes a lot more. And similar for gamma rays, 8 is about the average. So these are all things that you can measure, of course. You can measure the fragment charge, you can measure the masses, the kinetic energies. It's a little harder to measure this one, and we'll talk about that. And recently, there's been a lot of study on correlations between these variables, and the experiment I'm presenting here is no exception. So why are we studying them? It's really, really hard to make a predictive model of fission. It's a really complex reaction. I write here that there are competing strong nuclear and electromagnetic forces. There are a lot of time scales involved, and a lot of the time, theorists like when there's not a lot of time. It's really nice when there's a lot of experimental data with which to test your theories and hypotheses. But in the case of the initial conditions of the fragments right after the nucleus splits, there's not a whole lot of that. So that's what we're trying to address here. In terms of applications to other areas of nuclear physics, since I'm working on nuclear astrophysics now, I'll plug this one in particular, is that it's important for our process of nucleosynthesis. So one confirmed site of this our process, or the rapid neutron capture process, is neutron star mergers. This most famous event is the GW170817. This was when we first measured gravitational waves. And then there's also potentially another site in core collapse supernovae, but that has yet to be observed. The point is, though, that fission is kind of the endpoint of our process. Once something gets heavy enough, and the fission cross-section gets large enough, then you can't really go heavier than that. And so for thousands of potentially fissioning nuclei, if you want to make a reaction network or something, you need to have the fission barrier height and shape so that you can decide when fission occurs. The other component of this fission recycling, where we go up and up and up with neutron capture, and then we go back down because of fission, is the yields. And that's also difficult to predict. I asked ChatGPT to improve the picture it gave me first. There's still some problems with it, but at least there are only 2 fragments this time, and it took a little bit more of a space element, so I just decided to include it here. But anyway, to fragment initial conditions, these are still being studied. One example of an open question is the excitation energy sharing between fragments. So it was seen pretty early on that if you just assume that the fragments are at the same temperature, then you don't reproduce the observed neutron multiplicity curve as a function of the fragment mass. One thing that has yet to be measured at all is the opening angle between the spins of the fragment. So there are three components to the spin of the system. There's one fragment, two fragment, and then their orbital angular momentum. This is an interesting thing to study. But what I'm focusing on here is the correlations between energy in fission and then the magnitude of the spin of the fragments. And of course, it's not really feasible to measure all of these barriers and yields and things for all of the nuclei that might contribute to the R process, for example. So you need to make a model that you're confident can reproduce things at some extremes that maybe we can't always access in the lab. And that means measuring these quantities of the fragments so that we can test the models. So I'm really oversimplifying this, but I've kind of split models of fission into two different classes. The first I called phenomenological, and usually they have a set of input parameters that are fit to experimental data. And if there are spin energy correlations present, they usually come from a simple statistical model where the level density at the excitation energy that's selected is sampled, and then there goes your spin. Everything's encoded in this so-called spin cutoff parameter that usually has that's a somehow fits to the experimental data. And then you can try to model fission from as first principles as you can get and try to solve the time-dependent Schrodinger equation. To me, anyway, the connection between spin and energy from these is more murky. And in the end, you determine the spin by projecting out the wave function. But there you go. So part of what makes fission difficult to study experimentally is that a lot of the interesting stuff happens extremely quickly, and you really can't see what's happening inside. So the actual scission part from going from one nucleus to two is 10 to the minus 21 seconds order of. And so what we're really measuring in the end is, in the final state, is the neutrons that come out, the gamma rays that come out in the fragments. You can't really get much else. And so when we're talking about measuring spin and fission, we have to figure out how to reconstruct the initial point by what we actually can access. And that tends to be the fission neutrons, gamma rays, and what I didn't mention here is the fragments. So if you imagine that we start somewhere in this banana of relatively high spin and excitation energy, our fragment starts somewhere here. We're in a region of relatively high level density. So if we have enough energy, we can emit neutrons, and those will have somewhat Maxwellian spectrum. They're isotropic in the fragment frame, at least for fission of californium. And so those aren't going to remove much spin. Then come after the neutron separation energy is, well, after we're lower than the neutron separation energy, we get statistical gamma rays. Usually those are E1, and they're not always stretched transitions. So we can say with some confidence that they don't remove most of the fragment spin. What does remove most of the fragment spin is these discrete gamma rays, and they have some really nice properties for us to measure. They have identifiable energies, and especially for the more common fission fragments, we know the level schemes very well in this regime. So we can do spectroscopy to identify these transitions that remove most of the fragment spin. So I've picked out a few fission gamma ray measurements that I want to reference back to. The first was Chavar et al. They measured the multiplicity of gamma rays in fission in coincidence with fragment mass and with TKE, notably not at the same time. And they saw this gamma ray sawtooth pattern. This is the shape of the gamma ray multiplicity as a function of fragment mass. You may have heard of the neutron sawtooth, and it turns out it's a similar shape with mass. And they saw this TKE dependence where as you go lower in TKE, it starts to grow and then it levels out. And significantly, I want to point out that they didn't differentiate these two variables at the same time. And that'll be important to do. In the same year, the spin sawtooth in fission was measured for the first time. And in this case, it was exploiting gamma ray spectroscopy to actually find which levels of the fission fragments were being populated post-statistical emission. But this experiment did not have any sensitivity to the fragment energy like Chavar's did. And then this experiment that was published in 2024, it was kind of like Travar's, but it was unifying these two separate results of the multiplicity as a function of mass and energy. Now it's a surface differentiated with respect to both variables at the same time of the gamma ray multiplicity. And I'll point out a little bit later some interesting things that might come from that. But it's important to note that if you're just measuring gamma ray multiplicity, you have to work a little harder to connect that to spin. And that's why I say none of the measurements that I just showed can identify both spin and energy at the same time. So let's combine them. If we want to see whether this statistical population that's set forth by some of the phenomenological models is a good model, we should see how the spin distribution of these fragments evolves with their excitation energy. And so we'll do that with the following method. For the energy, we'll measure the total kinetic energy of the fission event. This is the complement to the total excitation energy. So it's a decent handle. And then for spin, not unlike the experiment of Wilson, we're going to measure the side feeding to low-lying nuclear levels in the fragments. So this is what the setup looks like, or at least one part of the setup. At Argonne National Lab, with a lot of help from the wonderful low-energy support group there, we built an ionization chamber that was purpose-built for performing simultaneous fragment gamma ray measurements. So I guess the cool part is that the anodes themselves, these green boards, are also a structural component. And from this, we can get the fragment kinetic energies, masses, fission axis, and ultimately the event-by-event energy. We put that inside of Gammasphere, which is a high multiplicity, high resolution gamma ray spectrometer in 4 pi around the chamber. And from this, we can do gamma ray spectroscopy, as well as the angle with respect to the fission axis, and reconstruct the spin distribution for certain fragments. And so I have a little bit of show and tell. This is our ionization chamber that was taken apart to load the californium source. You can see some small tears in the carbon backing. Thankfully, they're far away from the source spot, but yes, we were worried about that in case you were wondering. Here's a model of the ionization chamber inside of Gammasphere with only one side closed. I thought I'd just put this here. If you didn't know, Gammasphere is extremely famous movie actor. It was in the 2003 version of the Hulk movie. And then Doesn't look quite as nice as the picture, of course, but there's the ionization chamber loaded inside Gammasphere right before the experiment. So I talked a little bit about the ionization chamber already, but basically uh, there are two independent sides. The fragments are emitted back to back, and so you can get a measurement of each fragment's kinetic energy. And using what's called the 2E method, you can reconstruct from that the fragment mass, as well as with some other signals, the polar angle of the fission axis. So that means event by event, we can place our fission fragments on this graph where the axes are our mass and total kinetic energy. When we want to measure our gamma rays, we're looking at cascades, and the idea is this: we have a fragment that's where the low-lying level scheme is well known. And at some point, we stop emitting neutrons and statistical gamma rays and start emitting these. Once we get to this point, we know roughly what's going to happen. And so these levels are de-exciting pretty predictably. We can identify those, and based on the intensity balance between different gamma ray lines, we can reconstruct the distribution of states that are fed from the side, like this one. In this case, it was illustrated an event where this 8+ state is fed from the side. So, not to get too into the weeds, if we want to look at how the spin distribution for a specific fragment evolves with energy, we do the following. Put as an example, if we're studying barium-144, well, we have a mass measurement from our chamber. We'll gate on that. To clean up the gamma ray spectrum, we'll gate on the first excited state energy in Gammasphere, and then do some Doppler correction, some projecting, and then some fitting. And all of a sudden, we have gamma ray intensities as for each TKE bin. We can use the information that I talked about before, the intensities and the level scheme, to do this balance and reconstruct a spin distribution. Do that for every TKE bin, and you get something like this. So this is kind of the result for barium-144. And what I want to point out here is that this vertical scale is not very big. So the whole thing is a little bit more than 1 h-bar. And in terms of the points, when you vary TKE, going from high TKE to low TKE, or equivalently, low excitation energy to high excitation energy, as I'll justify in a minute, the average spin doesn't change that much. And in fact, it changes a decent amount less than what you would expect if you were going to generate spin based on some statistical argument. So I'm bringing back this gamma ray multiplicity as a function of energy plot from earlier, from Marin 2024. And it's a little more tenuous to connect this to spin, but if you look at the red points as a function of increasing excitation energy, it's also relatively flat. So these would seem to agree with each other depending on how you connect gamma ray multiplicity and spin. So I said something in the last slide that I need to justify, and that is that as you decrease the kinetic energy in the fission event, you're also increasing excitation energy. And if we look at a different paper where they measured neutron multiplicity as a function of total kinetic energy for different fragment splits, we see that barium-144 should be getting roughly half of the available total excitation energy. So we know that as we go down in total kinetic energy, the energy is coming into the nucleus, but it's it's not expressing itself with a large change in the fragment spin. And so I want to conclude on that note. We looked at these correlations between spin and energy to try and learn how fragments acquire their spins. In the end, we found that the fragment spin for barium-144 anyway depended pretty little on energy. And if we put this in context with a couple other fission measurements, it seems like the spin generation mechanism, which is often adopted in more phenomenological models of fission, appears to be more complex than that. And this data set is not over with, although I'm not working on it myself at the moment. The obvious next step is to do this analysis for more fragments. So I only got barium-144 done, but of course there are a lot of other fragments in that data set. We just did spontaneous fission. There are other analyses you can do, namely angular correlations, seeing if fragments are polarized with respect to the fission axis or if they're depolarized. What's the effect on changing the energy, on changing the mass, and so on. I think that if it would be nice to include the statistical gamma ray contribution somehow. This would require some models most likely, but this would also help to really include, well, another source of possible spin removal. And then if we had a nicer fission chamber, then we would, well, if we had it for the experiment, we could have maybe 10 times the statistics. So that'd be super nice. And adding a beam window would unlock so much additional study down the road. Being able to do similar studies with induced fission would be really interesting. So with that, I'll thank the funding agencies and open it up to questions. Thanks for listening.